Welcome to Brain Vision.
To estimate the energy uncertainty, we can use the following relation in the first item. So, the energy uncertainty multiplied by the average lifetime is bigger than or equals to h bar. Therefore, the energy uncertainty is bigger than or equals to h bar divided by the lifetime. Then, this is equals to 1.055 times 10 to minus 34 divided by the lifetime of 10 to the minus 8 seconds, and this is equals to 1.055 times 10 to minus 34 plus 8 minus 26 joules. We can convert the energy uncertainty from joules to electron volts by dividing by the electron charge, and by doing that we get the following. The energy uncertainty is bigger than or equals to 1.055 times 10 to minus 26 joules, or 1.055 times 10 to minus 26 divided by 1.6 times 10 to minus 19, which is approximately 6.59 times 10 to the minus 8 electron volts, or further approximating, this can be written as 10 to the minus 7 electron volts. So this is the energy uncertainty in electron volts, and this is the energy uncertainty in joules. You can choose whatever is more convenient. In the second item, we have to evaluate the transition energy from the level n equals 2 to the level n equals 1. Remember that the energy of the nth level is equals to minus 13.6 divided by n squared electron volts. Now, the transition energy from n equals 2 to n equals 1 is the same as the energy of the photon that is produced as a consequence of that transition. And the energy of that photon is given by E2 minus E1. Therefore, we can use this equation for En to calculate both E2 and E1 to get the following. E2 is minus 13.6 divided by 2 squared, which is 4. And E1 is minus 13.6 divided by 1 squared, which is 1. We have two minuses multiplying, so it becomes a plus. So we can write it as minus 13.6 times 1 over 4 minus 1. Then we get that this is equals to minus 3/4. Therefore, the transition energy is equals to 13.6 times 3 over 4, which is equals to 10.2 electron volts. Therefore, the ratio of the energy uncertainty to the transition energy is given by, let's call it delta. So we have delta is equals to sigma E divided by E to 1, which is equals to 10 to the minus 7 divided by, we can approximate this 10.2 to 10, so divided by 10, and this is equals to 10 to the minus 8. So the ratio is approximately 10 to the minus 8. Remember that both this 10 to the minus 7 and this 10 are approximations, so this is why we have an approximate sign here. On the last item, we have to calculate what is the wavelength of this transition. Well, remember that the energy of a photon is given by age times the frequency of that photon. And then remember that the frequency of a photon times the wavelength of that photon is equals to the speed of light, c. Therefore, the frequency is equals to c divided by lambda. We can plug in this relation in this equation to get the following. The energy of the photon is equals to h times c divided by lambda. Therefore, the wavelength of the emitted photon is equals to h times c divided by the energy of that photon. Now, that photon is emitted as a consequence of the transition from n equals 2 to n equals 1. So it has an energy of 10 0.2 electron volts, as we had just calculated. Therefore, plugging in these values for the wavelength, you get the following. The wavelength is equals to h, which is 6.63 times 10 to minus 34, times the speed of light, which is equals to 3 times 10 to the 8, divided by the energy, which is the transition energy that is given by 10.2 electron volts. So to use this in this equation, we have to convert from electron volts to joules, and we can do that by multiplying the quantity in electron volts by the electron charge, which is 1.6 times 10 to minus 19. So we multiply it by 1.6 times 10 to minus 19. And this gives us a wavelength of approximately 1.22 times 10 to the minus 7 meters, which is equals to 122 times 10 to minus 9 meters, which can be further written as 122 nanometers. This is the wavelength of the emitted photon. Now we have to calculate what is the width of that line in the spectrum. The width of that line is given by sigma lambda, which is the uncertainty in the wavelength. And we have a relation between the wavelength and the energy. So we can relate the uncertainty in the wavelength with the uncertainty in the energy by taking the derivative of this relation. So taking the derivative of lambda, we get d lambda, and this is equals to h times c, because they are just constants, divided by e squared. There is a minus sign because of this derivative of 1 over e, times dE. Now we can identify d lambda with the uncertainty in the wavelength and dE with the uncertainty in the energy. Therefore, the uncertainty in the wavelength is given by, let us work with the absolute value. The absolute value of the uncertainty in the wavelength is given by h times c divided by e squared times the uncertainty in the energy, the absolute value. Now, note the following. We have h times c divided by e here. So we can actually write this again using this equation. So note that h times c divided by e is the wavelength. So we have this is equals to h times c divided by e times 1 over e to make the e squared times the uncertainty and the energy. This term of h times c divided by e is equals to the wavelength. Therefore, we have that the absolute value of the uncertainty in the wavelength is equals to the wavelength itself times the uncertainty, the energy, divided by the energy. And now we have to plug in the values. So this is just the value of the wavelength we have just evaluated, which is given by 122 times 10 to minus 9 meters. Now we have to plug in the value of the energy uncertainty and the energy, but we had already calculated this ratio on the last item of this equation. This is given by this equation. And we know that this ratio is given by 10 to the minus 8. So we have this times 10 to the minus 8, which can be approximated to 10 squared times 10 to minus 9 times 10 to minus 8, which is equals to 10 to minus 15 meters. But we can write 10 to the minus 15 meters as 10 to the minus 9 times 10 to the minus 6 meters. But 10 to the minus 9 meters is just a nanometer. So the uncertainty in the wavelength, which is equals to the width of that line of the spectrum, is equals to 10 to minus 6 nanometers.